Hello, and welcome to Lecture 4 of the Interactions Unit in Phys 1104. In this lecture, we're going to get into lots of detail about potential energy. So in an earlier lecture, I claimed that the ratio of accelerations of two interacting objects is the negative inverse ratio of their inertias, just like we've seen for delta v's. And let me just prove that, because it's going to be an important principle for us going on. So we know that for an isolated system, this is true. This is just another statement of conservation of momentum. And so I can write that out this way. Let me, because the interaction takes place over the same amount of time for both of them, divide both of these by the delta t that it takes place in. Now, what I can do at this point is take limits of both sides as delta t goes to 0. So I'm simply considering small time intervals during which these delta v's are small and these delta t's are small. But that is by definition just the time derivative, right? So this is dva by dt, and this is dvb by dt. But again, by definition, that is the acceleration. And so now what I just have is and you can certainly rearrange that and just look at the x components and come up with this relation. For any closed system, by definition, the total system energy is constant, or in other words, the change in system energy is always 0, and we can express that as a sum of the change in kinetic, potential, source, and thermal energies. If the system only has non-dissipative interactions, then there can't be any change in source energy or thermal energy because those involve dissipative interactions, and so the expression simplifies to the change in kinetic energy and the change in potential energy add up to 0. And we've already seen earlier, briefly, that we call kinetic energy and potential energy together mechanical energy, and we distinguish them because they're the two forms of energy that can be reversibly transformed back and forth into each other. So that means we can summarize the condition for a closed system with non-dissipative interactions as that the change in mechanical energy of the system is 0. Whenever there are no dissipative interactions, all the processes in our system are reversible. And that reversibility is going to turn out to have really important consequences to us, so let's have a close look at it. Here's a cart colliding with a spring which is attached to a wall, and I've included the cart, spring, and wall in my system because I want to be able to define a spring potential energy, and so I have to include every object that the spring interacts with. And here it is in reverse. Everything looks exactly the same, except that our clock seems to be running backwards when we view this in reverse. And in particular, notice that these two times that I've called t2 and t4 are exactly the same. Here they are again down here. I've just chosen two times when the spring compression is the same, and by the reversibility of the process, that means everything else has to be the same too. In particular, the potential energy has to just depend on the state of the spring, which is just its length. Or I could talk about it in terms of the position of the cart relative to the wall, because that also defines the length of the spring. And notice that that relative position is the same at time 2 and at time 4. The easy kind of energy to measure is kinetic energy, because it just depends on speeds, which are easy to measure, and inertias, which are easy to measure. But because of the closed system, we can determine changes in potential energy if we know changes in kinetic energy. And so in particular, if we've defined the spring potential energy to be 0 when the spring is relaxed, then we can say that the spring potential energy at time 2 is the same as the spring potential at time 4, and the way we would actually measure it to prove that would be by measuring kinetic energies. Well, this applies to any pair of times, not just 2 and 4, with the same relative position of the cart to the wall. And so that means that the potential energy must only depend on the relative position of the cart to the wall. So I could just define my axes at the wall, and now the position of the cart determines the potential energy of the spring. That's a good choice, but it's actually a better choice to define my axes this way. I'm going to deliberately put the origin of my coordinate system at the location where the end of the spring is if the spring is relaxed. Now with this choice, since the position of the cart determines the length of the spring, we can say that the spring potential energy is just a function of the cart's position x. This is not just true for spring potential energies, it's true for any potential energy. Any potential energy always just depends on a relative position between 2 interacting objects in the system, and if only one of them is moving, then we can always rewrite that as a function of just the position of one object. If we were to actually measure and then graph the potential energy function, it would look something like the green curve above, where note that I've showed that the kinetic energy and the potential energy have to add up to the constant mechanical energy in this closed system. And I've made it so that at the end where the cart is stationary, that is where the kinetic energy is 0, and at the other end where the potential energy is 0, that's where the spring is completely uncompressed. And let's also think about some place in the middle, and I'll name these 3 places x1, x2, and x3. Notice that in passing from x1 to x2, the cart has slowed down. We know that because its kinetic energy decreases from x1 to x2, and so it must have been accelerating back that way. Similarly, going from x2 to x3, it's still slowing down. The kinetic energy decreases further, and so it's also accelerated back that same way. Well, in both of those cases, the acceleration vector is pointing back towards locations where the potential energy of the system is lower. This is a general rule. The parts of a closed system always tend to accelerate in the direction that lowers the system's potential energy. This may seem sort of abstract at the moment, but it's going to turn out to be really important. In fact, as we'll see in Phys 1204, you cannot understand the operation of electrical circuits without understanding this. Here are some experimental facts, some of which you already know. On Earth, near the ground, as long as we can ignore air resistance, all objects accelerate at about 9.8 meters per second squared down. You might not realize, though, that the farther from the ground you get, the lower that acceleration is, so that, for example, 300 kilometers up, it's about 8.9 meters per second squared, and out in geosynchronous orbit, it's down to 0.22 meters per second squared. Well, that's too complicated. Let's restrict our attention to situations where we're close enough to the Earth's surface that we can say that the acceleration due to gravity doesn't vary with height. Now, you've probably seen gravitational potential energy in an earlier course, but you probably haven't seen why it's actually possible for us to define it. So, let's think about throwing a ball upward. Of course, it slows down, momentarily stops, and then falls back down, speeding up. And in particular, you already know and can verify experimentally that at 2 places in its path where it's at the same height, it has to have the same speed. So let's look at the consequences of this, and it's going to be a lot like the cart hitting the spring. The ball is accelerating, so it must be interacting with something. You can do experiments in vacuum, and this all happens the same way, so it's not interacting with the air. In fact, it's not touching anything, so this must be a long-range interaction. And it works the same way everywhere on Earth, so clearly the thing it's interacting with is the Earth. Also, this fact that it's at the same speed whenever it's at the same height says that this is a reversible process. And so this interaction must be non-dissipative, and we can associate a potential energy with it. If we're going to do that, then we need to include the interacting objects. That would be the ball and the Earth. And so to define a gravitational potential energy, we have to include the Earth in our system. So we have reason to believe that there should be a potential energy function for the gravitational potential energy, and it should depend on the relative position of the ball and the Earth, which is just defined by the height of the ball. We can actually define that as a height above any point we want, but for now let's think of it as height above the ground. And let's find it using the fact that our change in gravitational potential energy has to be the negative of the change in kinetic energy. So I'm just going to write it that way, and I'm going to write my kinetic energies in terms of y components of velocity, as long as the ball is moving vertically. Those are the same as speeds. And now I'm just going to factor out the 1/2 m, that's a common factor. And now I'm going to note that this is a uniform acceleration situation, and so all our equations of uniformly accelerated motion should apply. And in particular, look, I've got squared components of velocities. So I would think that this equation here ought to be useful to us, and in particular, that a is just negative g. So I can rewrite this as, and now I can just substitute this in here. And so when I do that, I can do some cancellation. The negatives cancel, the half cancels out the 2, and I'm going to multiply through, and I get this expression. And note that I expect that to be of the form a gravitational potential energy final, or as a function of y final, minus a gravitational potential energy y initial. And indeed, that's exactly what I have. Here is the one piece, and here is the other, and so I can just read off that my gravitational potential energy as a function of y must just be mgy. As long as we're near the Earth's surface, let's work a problem very similar to a situation you've seen during an activity in class. So here we have a spring-loaded gun. We know the spring potential energy stored in the spring, and we know the inertia of this ball. And the spring is going to release and launch the ball upwards. And I'm going to define our system to be the ball, the spring. We need everything that the spring interacts with, and so I need the floor. And we want to be able to use gravitational potential energy, so I'm going to include the Earth in the system. And when you did this in the activity in the class, the Earth wasn't in the system, and so you couldn't define a gravitational potential energy. Well, initially, there's going to be a lot of spring energy. Also, the ball is a little off the floor, and we've defined the floor as the place where y is 0, so it has a little bit of gravitational potential energy as well. And then at the end, it has no spring energy. The spring is fully extended. It's momentarily stationary at the top, and so it has no kinetic energy either, and so all it will have is gravitational potential energy. And so that gives us our conservation of energy equation. It's just going to be the whole initial US plus UGI, all equals our final UGF. And we know US, it's just a number. And we know UGI, but I'm not going to write it out. What I'm going to do is I'm going to substitute in the expressions. And so now I can do a bit of rearrangement here and say that now I can substitute in numbers. So I know this is 10 centimeters, but I'd better work in meters. Inertia is 50 grams, but I'd better work in kilograms. And g I'll use, as I usually do, just 10. If we needed more precision, we could get it. And if you plug that all into your calculator, you will get 1.3 meters.